All right, everyone. So welcome back. Just that. Welcome back. So we're gonna start the chapter 2 videos now in terms of the summer work. The first one we're gonna do is on early chemical law. So I can describe the law of conservation of mass, law of definite proportions, and law of multiple proportions. Just to remind you guys, if you need to, go ahead and stop the video, pause, so you can write things down. You don't have to watch it in real time. I'm just going to continue to work right through the video with the expectation that you would have to probably pause it to write things down and things like that. So when we're talking about early chemical law, I'm talking about some things that kind of came along early 1700s that pushed us towards the model of an atom. So we know that there's atoms. We've been taught that. You've been taught that since the 4th or 5th grade, but it wasn't always understood that the universe was made of atoms, or matter at least was made of atoms. So let's just real quickly talk about a couple of people that got us to that. The first guy I want to talk about is Antoine Lucifer. He was a French chemist. Was around in the late 1700s and was the first did a series worked on a series of chemical reactions that led him to the conclusion of the law of conservation of mass. He basically came up with the idea that mass could not be created or destroyed. Okay, so mass, or better yet, I'm going to change this right into matter here, is that matter cannot be created or destroyed. Now, this was kind of a big deal because prior to this, it was thought that that is something that could potentially happen. For example, when people used to combust things, they thought oxygen was eaten up and a substance called phlogiston or something like that was produced, essentially changing things from one state to another. And this kind of falls in line with pre-1700 notions of alchemy. Alchemy was the science behind changing precious metals into gold or useless metals into gold. We're just going to kind of ignore the chemistry that occurred before the 1700s. It wasn't particularly useful. It's interesting, but not particularly useful, so we're going to go ahead and skip it. At this point, I'm hoping that most of us have heard this idea of the matter that cannot be created or destroyed. So we're going to kind of move right through that. Next, we have a guy named Proust. I forgot to write down his first name. I'd have to look it up. He, similar time, a little bit later, lived to be a very old man, which was kind of unusual in those times and days and age, but wait a minute, that can't be right. He lived to be, oh no, that's about right. Alright, so 98. He came up with the idea of the law of definite proportions. Like Antoine, he did lots of chemical experiments and was very meticulous about the way he did them. How much he put in, how much they weighed when they came out. And what he would do is he would take chemical compounds and decompose or figure out what they were made of, and then measure the ratios of one thing to another. Now you gotta understand, at this point, we're still stumbling upon the idea of atoms. Elements are misunderstood at best. You're looking at basically trying to figure out the fundamentals here. So he took something like water. Now, we all know that water is composed of H2O. But back then, they had no idea what water was made of. They just knew it was water. Now, what he noticed is if he took water and he split it, he got hydrogen gas and oxygen gas. Now, once again, I write H2 and O2 for those, but they had no idea what the chemical structures were for these. So this was actually beyond their comprehension. So we'll change this to, he just knew that they got hydrogen and oxygen. and it was hydrogen gas because of the properties it had. It was oxygen gas because of the properties it has. Back then, we only knew the macroscopic properties of our elements, and that's what everything was based on. And then what he did is he noticed that if he decomposed this, for every 1 gram of hydrogen he produced, he always produced 8 grams of oxygen. If he produced 2 grams of hydrogen, he would have produced 16 grams of oxygen, and so forth and so on. But what he'd always noticed was the ratio was the same. So this was always for water's case was always a 1:8 ratio. Now Proust, being a smart chemist, said, "All right, so I'm going to propose a chemical formula for water." Now he wanted he didn't propose a chemical formula for water. He just knew that this said that hydrogen must have been 8 times lighter than water was. Or an oxygen molecule was 8 times heavier than a hydrogen molecule, which turns out not to be true. But he was on the right track, which actually led to what our good friend Dalton did. So let's get a real quick definition here. Proust's law of definite proportion says that the same compound always contains exactly the same portions of constituents, that's definitely not spelled right. Oh, the same proportion of constituents by mass. And when I say constituents, I mean what it's made of. Alright, so where do we go from there? Well, the next thing we got is, let's just kind of keep track of our people here. We've got Anton Lucifer, we've got Proust, and now let's talk about our good friend John Dalton. Now, what John Dalton came along with was what we call the law of multiple proportions. So what he did is he took a series, I'm off the screen, sorry about that. He took a series of chemical compounds and compared their ratios. So he took things that they kind of knew were composed of the same thing. So for example, he took something like carbon monoxide, carbon dioxide, and something like a carbonate. Okay, once again, I'm writing chemical formulas. John Dalton had no clue what these things were made of. All he probably would have been able to conclude at this point is that these things were made of carbon and of oxygen. So what he did is he said, well, I'm going to take this and I'm going to force it to decompose. And I'm going to force it to decompose to the point where I have, let's say, 12 grams of carbon. And I'm going to do the same thing with carbon dioxide and the same thing with this carbonate compound that we all know that he could conclude were all made of carbon and oxygen. And what he did is then he looked at how much oxygen came out. And for something like CO, he would have seen 16 grams. For something like CO2, he would have seen 32 grams. And for CO3, he would have seen 48 grams. What he noticed here was, minus the fact that remember, once again, he can't see these structures. He doesn't know what those are. What he noticed here was that the differences, or the ratios between these, were always whole numbers. 48 over 16 is 3. 32 over 16 is 2. So it always gave us these nice whole round integers, which led him to conclude that the difference between these compounds must have been a unit, a single piece that contributed exactly that much weight each time, which he wasn't far off. The idea here is definitely the fact that what he would end up concluding is that you're adding an oxygen each time to each one of these compounds. That's why we see the weight going up despite the number of carbons staying still. And he did this for a series of compounds to come up with this idea. He just found that compounds of a series, so here we go, definition again, do this one in green. Compounds in a series always produce whole number ratios. Now, if you look in their book, they've got a little more detailed description, probably a little more correct. I mean, arguably correct. But the key piece here is that you understand what Dalton was able to come up with here. Is this idea that looking at these whole number ratios, he could conclude that oxygen was being added one at a time to these different compounds. It was never 3.5 or 3.25 or 2.3. It was always these nice whole round number ratios. So that kind of implied, like, once again, that you were adding a whole group of oxygens. Now, could it have been adding one group or two groups or three groups? Yeah, and he had no idea. He actually, John Dalton, back in his day, when he was studying water, originally thought that water was composed of a single O and a single H, which we know is not true today. So that's our first little introductory on early chemical law. These guys are important fundamentally because everything we talk about holds true, but they're also things that we probably learned to be true from an early age. So we're not really stumbling on new territory here. In the next video, or in a couple of videos, we'll talk about the modern theory from the 1700s here, this early 1700s period where John Dalton and them came through, to where we are now in terms of the atomic model. By the way, John Dalton was a 1766 to 1844, so he was right here in that period when all this was going on. Alright, so that's the first video in the series for Chapter 2.